Welcome learners. In today's lecture, we are going to conclude the fifth chapter that is talking about the materials in the form of conductors and dielectrics. We are going to look into some important aspects of the material properties when they are interacting with each other, especially in the field of electromagnetic theory. Boundary conditions is something that we should know, that how the waves behaves when they are crossing from one boundary to another boundary. So we are going to look into the boundary condition for conductors. What are the values of the fields? By fields we mean what is the behavior of the electric field intensity and the electric flux density when we have two materials that are conductors and free space. And then we are going to look at the boundary condition for the dielectric materials in the form of the fields, again, that is the E field and the D field. And then along the way we are going to look into some of the equations that are associated when dealing especially with dielectric materials, and that is the polarization or the dipole moment. So let us begin by first looking or understanding some of the properties related to conductors under the static conditions. That will be helpful when we analyze the boundary conditions of conductors and free space. So whenever we have the conductors and we are talking about the static conditions, we know that conduction happens because of free moving charges, or called as electrons or free charges. And normally the lattice structure is such that no opposition is given to these charges and the conduction can take place. Either they collide with each other to produce heat or they pass through them. Now some of the properties that we want to consider when understanding the boundary conditions, especially for conductors. Under static conditions, we keep in mind that whenever we have any conductor and we have static conditions, which means that the electrons are not moving, they are stationary. So no charge is going to exist inside the conductor. If there is no charge, it means there is going to be no electric field generated. So no charge equals to no electric field inside the conducting material, because we are considering the static conditions. The second thing that we have to remember based on our previous understanding, that the charges will only exist on the surface of the conductor, and they will be represented as surface charge density, which is rho of s. So inside the conductor, the charge density will be 0, but the charges will be available on the surface of the conductor. Since the surface will have charges, it means that the fields, either electric flux density or electric field intensity, will always be normal to that surface. So if this is the surface of the conductor and the charges are available on it, then the flow or the direction of the fields will be normal to the surface. Finally, the surface charge distribution basically is defined as per shape of the object. So if we have a straight object or a conductor, then the charges will be on the surface in this form. If this is arbitrary, then the charges will follow this structure. So it depends upon the shape. And ideally, any conductor will have an infinite conductivity, but that is an ideal case which we normally utilize in solving some problems or equation. And finally, since we have surface charges on the surface of the conductor, then all these charges will behave as an equipotential surfaces. Again, equipotential surfaces is something where we have the same potential on the surface, or they have the same values of the potential, or the potential difference between them is 0, or they have the same potential. So this is known as an equipotential surface. So these are the 6 points that we have to keep in mind, and these will be helpful once we go into the boundary conditions analysis for conductors. Another thing that we want to remember is that whenever we have a conductor, there are free electrons inside it, and as soon as these electrons, as per Coulomb's law, come into close vicinity of each other, since they are all negatively charged, they are going to repel each other, and thus nothing will be inside the conductor. So the point where we said that that there is no charge inside the conductor, and thus there will be no electric field inside the conductor. So one way to understand is based from the Coulomb's law, because since all the negative charges will repel each other, they will just move to the surface or near the surface of the conductor, and hence the point where we said that charges will be available only on the surface of the conductor is also verified from this explanation, which was given to us by Coulomb's experimental law, and we have seen already. that these charges will appear on the surface as well. So this is a visualization of the points we have seen previously. So before we go into the boundary conditions, we have to keep in mind that we basically want to understand what happens if we have two materials. Let's say we have material 1 in the blue box and material 2 in the yellow box. So we want to know what happens in the material or the second material along with the properties of the first material, and we want to see what happens to the fields once they cross this boundary. So we will have a boundary between two materials, and we want to see the behavior of the electric field and the electric flux density in both of these materials. So the thing that we are going to begin our analysis with is that whenever the field or a signal or a wave is available in the first material, we disintegrate these components or these fields into its components. One will be the normal component as d of n and e of n, and other will be the tangential component with d of t and e of t. So these are the components of vectors d and e. Now what is going to be the behavior of these components from the first material crossing this boundary into the second material? So this is what we normally do when we talk about boundary conditions between materials. So let us begin our analysis in finding the behavior of the vector fields, that is E field and D field, when they cross from one medium to other medium. We first start with the conductors boundary condition and we understand what happens. So in order to understand this, we create a medium. Let us say this is our boundary. So this is our boundary, and we have material 1 over here. So let us say this material 1 is free space and the second material is the conductor. So now we want to see the behavior of the waves interacting between free space, which is our first region, into the conductor, which is our second region. So let me call this region 1 and this is region 2. Now what we want to see that what is happening to the D and E fields when we move from free space into the conductor. So in free space, let us say this is the tangential component of the electric flux density. Let me call this as d of t, and this is the normal component of the electric flux density, and obviously the vector d will be in this location. So this is the components of the magnetic electric flux density, and in order to analyze this component, we basically take help of the Gauss's symmetry of a symmetric shaped cylinder. So this is going to be helpful to us. So this is its surface S, and it has a very small height, so we can say delta H. Half of the height is lying in free space, another half is lying in the conductor, and charges are normally on the surface. So this is the medium where we want to do the analysis basically. And on the other hand, let us take the electric field as well. So we can say that the tangential component of the electric field is as such, E of t. The normal component is over here, E of n, and we can say that the original E vector is as such. And in order to do the analysis on the E field, we are going to use the rectangular shape behavior that is closed in the points from A to D, and the width is delta W, and it has its own height, which is delta H. Again, height is having certain portion in the free space, so this is our free space, and other is in the conductor. Same goes for the cylinder as well for the electric flux density. So this is the image that we are going to use to do our analysis. So the idea is that we want to do the analysis of these fields in two ways. The first is we are going to find the equation for the tangential components. For this, we begin our analysis with the E field, which means we will find the tangential component or effect of the E field in the free space and conductor. And once we have this E field, we can also extract D field from this, because we know that the relationship between D and E is something like this. So this is very helpful. Then in the second part, we are going to do the normal analysis or normal component of the field, And for this, we'll begin our analysis with the electric flux density, and once we know the electric flux density, we can find the normal component as well. So this is basically this strategy that we are going to use. So let us first start in finding the tangential component of it. See what is the expression of the tangential component. And for the tangential component, we are going to focus on the E field, which means that, let me draw this boundary again. So this is the boundary, and I'm just focusing on the E field. So our analysis will be based on this rectangle that has a width of delta W, a very small height. Some portion of the height is inside the conductor, so I'll write it. This portion is our conductor. And again, why I'm stressing on the conductor, because the properties we have seen will be applied. This is the conductor portion, this is the free space, and we know we want to find the tangential component E of t. Then E of n is not required, and these are the components of the electric field. So we are focusing on the tangential component, which is we need to find E of t. Once we know E of t, d of t will be figured out from the main equation. So in order to begin the analysis, let us say we have a charge q, and it starts to move from point A, and it will cover this complete loop from B to C, C to D, and again back to A. So it's a closed loop. So since it's a closed loop, we know that the electric field moving in a closed loop is represented by the conservation of electric field equation, or around a surface, where E dot dl equals to 0. And using this, we know we can then integrate from A, then A to B, then B to C, then C to D, and again back from D to A, and we apply E dot dl on all of these things, and it should be equal to 0. So this is what we are going to do for all these sections. So we begin our analysis first from A to B. So let us say we begin integrating from A to B. Now what is happening from A to B? In A to B, we are going to move in this direction. So if we are moving, we know that electric field value in this case is, so try to match this motion of A to B along the boundary. We can see that E of t is parallel to A to B, because we are moving in this direction. So we can write it as E of t when we are moving from A to B, as it is parallel. Then what is dl? Now dl is basically going to be your width, it is going to be delta W. So this is the incremental length that we have covered from A to B. So this is the first solution. Now let us go for the second part. So in the second part, we have to move from B to C. Now B to C, we are moving in the downward direction, and if we compare it to the electric field, if this is our downward direction, we can see that it is opposite to E of n. So it is negative E of n, and it is covering a certain height. You can see the height is over here. So the height is delta H by 2. So why we have taken half of the height? Because this height is basically half of the portion is in free space and half is inside the conductor, and we have seen that inside the conductor there is no charge, hence there is no electric field. So that's why I've taken just half of the height. So this is from B to C. Then we go from C to D, and we can see that C to D is this direction, which is completely inside the conductor, and we said that there is no charge, hence no electric field, there is no motion inside the conductor, so it is going to be 0. Plus then finally from D to A, this is opposite to B to C, so it is going to be your E of n, because it is now moving in the same direction towards E of n, and then your height will be again delta H by 2, and it all equals to 0. So this is how the equation is formed when we move from A to D in a closed loop. So now we simplify this. So our equation can be written as E of t delta omega minus E of n delta H by 2 plus E of n delta H by 2 equals to 0. So this and this will cancel out. We'll be left with E of t delta omega equals to 0, and we can say that E of t will be equal to 0. So the tangential component of the electric field when we have materials of free space and conductor is equal to 0, and since E of t is equal to 0, this means that the electric flux density's tangential component will also be equal to 0 as per our basic equation. So these are the two equations that we should remember, that whenever we are dealing with the boundary conditions between conductors and a free space, the tangential component of the electric field and the electric flux density, which is E of t and D of t, is always equal to 0. Now let's come to the second part and find the normal component. So in order to find the normal component, I'll redraw the image over here so we can better understand it. Now we want to understand what is the normal component of both the fields. Normal component, let us redraw the image for better understanding. Again, we have the same boundary. This portion below is the conductor and this is the free space. And now we have the tangential component of the electric flux density. This is the original D, and then we have the components of D of N and D of T. For the analysis of this, we are going to use a cylindrical shape with the symmetric Gaussian symmetry. This is the top surface. The charges are lying on the surface because we know nothing is available inside the conductor, and this is the height, the total height that we are going to use. So again, just a reminder, charges inside the conductor is 0, which means that electric field is also equal to 0. So you have to remember this, for especially for conductor, and the charges are only lying on the surface of the conductor, which is the boundary in our case. Now in order to solve this, we use the Gauss's law. So Gauss's law says that the total charge is basically the present or represented as the surface charge density of the electric flux density in the incremental surface. Now, what is the incrementation or the integral that we can use? Since we have a cylinder, we know that it will have charges on the top, it can have charges on the bottom, and it can have charges on the side. So the charges are on the top, this is rho of s, it can have it on the sides, and it can have it on the bottom. Since the bottom is inside the conductor, so we don't need to use that, and the sides are not important to us because electric field is always normal to the charges. So if we are talking about electric flux density, it will always be normal to the top surface. From here, the normal to the surface will be like this, and this is not our direction of the normal because our direction of the normal is vertical over here. So we are not going to focus on the side of the cylinder as well. So we are only left with one integral, and that is the top. So we can say that the top will have what kind of a behavior? So then Q will be, you just integrate the top surface, and this means that Q is equal to, now what is on the top? So the top has a rho of S, which means that it will have electric flux density in the normal at that surface, which is delta of S. So this is basically the surface delta of S, which is lying on the azimuthal plane. So this is delta of S. Now what is surface charge distribution for terms of Q? So we know it is rho of S per charge, and then this is the normal element. We can get rid of charges, so the electric flux density normal just relies on the surface charges, which means that our electric field normal will just be the electric flux over rho of S. So, and we can also, or the book also writes d of n as En into epsilon naught, which is equal to rho of S. So this is what we are getting for the electric field and electric flux density normal, that it relies on the surface charges, and it makes sense that the charges are only available on the surface of the conductor, and which means that charges are only available over here, and these are surface charges represented as rho of S, and we have mathematically seen it over here as well. So to conclude, we have to remember that whenever we are dealing with boundary conditions, especially for conductors, the electric field intensity and the electric flux intensity for the tangential component will always be 0, and the normal component will be equal to the total amount of surface charge distribution, and this goes for E of n as well. So this is what we have to keep in mind. Now let us look at an example to better apply these boundary conditions. So in this problem, we have been given a potential field V as 100 sine hyperbola 5 of x sine hyperbola 5 of y, or sine of 5y, and at point 1, point 2, and point 3, and we have to find P. So we have to find at point P the potential, the electric field intensity, the magnitude of the electric field, and the surface charge distribution. If it is known that point P lies on a conductor surface, so we have been given a hint that we have a medium or a boundary between free space and a conductor surface. So what we have seen previously will be applied over here. So let us find the solution of this. But first it's better to visualize this. So we have a boundary that is between free space and conductor, and the point is lying, let's say, somewhere over. This is point P with the value of point 1, point 2, and point 3. Now we need to find at this point what is happening. So if it is point P, we know that its normal component will be over here and its tangential component will be along the surface of the boundary. So in order to find V at point P, this is the first part. So it's very easy. We have the value of P, just input the value of P in that equation. So value of V is 100 sine hyperbola 5 of x into sine 5 of y. What is value of P over here? So Vp is equal to so it is sine hyperbola 5 of x is 0.1 and sine 5 of multiplied with 0.2. So you solve this. Always keep in mind, when you are dealing with hyperbola value, your calculators should be in radian. So calculators should be in radian mode just to get the answer. Okay, this is for hyperbola. Okay, so once you solve this, you will get 43.8 volts. So this is the solution to the first part, that you find the value of V at point P. Now in the second part, you have to find electric field intensity. So that's very easy. We know that electric field intensity can also be figured out if we take the gradient of the potential. So gradient of potential means we need to find delta V. So delta V is basically the partial derivative of V along x for A of x, then partial derivative of V along y, A of y, and then partial derivative of Z along A of Z. So in the question, we already know that we have the value of x and y, so Z is not there, so we don't need to solve for this. Now what is the partial derivative of V with respect to x? So we write as 100. So 100 is the coefficient will remain. Then we have sine 5y, and then it will be sine hyperbola 5 of x, so it is going to be cos hyperbola 5 of x multiplied with 5. So this is the derivative along A of x for the first part. So we can say this is for the first part. Now let us find the partial derivative for the second part. So for the second part, it is going to be similar to the first one, so it is going to be 100 sine of hyperbola 5 of x, and then you multiply it with sine of 5y, which is cos of 5y multiplied with 5. So this is the partial derivative of the second term, which is over here. Once you have this, so we can write electric field intensity is going to be, you have all the values, just so this 5 is going to be multiplied, so you will have negative 500 sine of 5y, then cos hyperbola 5 of x along A of x, minus you multiply 5, so it will be 500 sine of hyperbola 5 of x cos of 5y along A of y volts per meter. So this is the solution of the second problem, and hopefully we are getting the same. So if you solve this, you will get the value. So I haven't multiplied it, but this is what you are getting. Okay, you can get, or you can reach to part B if you input the value of P in equation of E. So you put the value of P in X and Y in the above equation, so you will definitely get the answer, which is part B. So let us move to the third part, which is the magnitude of E. So that is easy. Whatever you have the answer of E, you just take its absolute. So you will get the answer of 495 volts per meter. So this is an easy part. And for the final part, you have to find surface charge density, rho of S. Okay, so rho of S. So rho of S, we have different equations now, but just related to our previous explanation of boundary conditions. We know that the normal conditions are always equal to the surface charge density. And we also know that d of n can be written as epsilon into E. So once we use this, because we already have the magnitude, you multiply it with epsilon, so you will get the answer. And that comes out to be, so I'll just write the values. So rho of S is equal to epsilon naught is 8.85 into 10 raised to power minus 12, and you multiply it with 495. So your answer will be 4.38 nanocoulomb per meter square. So this is the solution to the final part of this problem, and here we have utilized in part D the boundary conditions value, and this is hence very easy to utilize. Again, keeping in mind that the normal components will exist and the tangential components for the conductor boundary condition will always be equal to 0. Now let us come to the second part of this chapter, that includes the topic of dielectric or insulator materials. So before we begin, a comparison table has been shown that what are dielectrics and what are insulators. In a general way, dielectrics are materials that are very poor conductors because they are unable to conduct, since there are no free electrons. So remember that conductors are able to conduct because they have free electrons in their structure. But when we talk about dielectrics, or later on we see insulators, they have what we call as bound charges. So they are called bound charges because these molecules are bounded to the structure or the material so tightly that it becomes difficult for them to be free from their bonds. So dielectric materials are those that in which when we apply the electric field, they form dielectrics, or what we call as polarization, and they have minimum losses. And in insulators are those materials that have low conductivity and they have obstruction in their flow. So if we have a material and the charges want to flow, they will face different obstructions. In dielectric materials, as the name suggests, polarization means, which means that we have formation of positive and negative poles inside the material itself. And insulator is something which doesn't form this polarization. The bonds are weakly bonded, so an external electric field can mobilize them, as compared to insulators that form covalent bond. The dielectric constants is the value of dielectric is very high, and for insulators it is low. So what is dielectric constant? Normally it is the material properties which has certain values like 2 to 100. So this is the property of the material which we call as a dielectric constant. Dielectric materials are especially utilized if you want to store energy. How they store energy? Because if we have a dielectric slab, let's say this is a dielectric slab and it has charges which are strictly bonded, or they are bound charges. So if an electric field is applied, so basically these charges slightly shift. So if this is a negative side, this is a positive side, so they slightly shift. So this shifting creates some vacancy where the energy can be stored. So that's why dielectric charges store energy. Insulators cannot do that, and some of the examples are shown over here with their application. So you can have a go through this table to have a better understanding between the comparison of dielectric and materials. In our case, we will be talking about dielectric materials, and we already said that dielectric materials are such that have bounded charges, and which means that these bounded charges can create what we call as dipoles. Dipoles meaning that they can create, or they have positive and negative charges between them. There are no free charges, that's why these materials don't conduct, and their charges are strongly bounded to their atomic or molecule structures, and if you apply an electric field, they are just slightly moved. So insulators visualization, would be something like this, that if you have an atom, we know at the center it has nucleus and these are electrons. In a dielectric material or insulator, these electrons are tightly bounded to their structure, and if you apply an electric field from the outside, the materials create what is known as a dipole moment or dipoles. So again, dipoles is creation of two charges, that is positive and negative, and their combination is known as a dipole moment, represented by a small alphabet p that depends upon the charge and the distance between them. So this equation is for the dipole moment. Again, we are going to look at some of the equations, but we are not going to prove them. So dipole moment exists when a dielectric material gets excited by an electric field. The electric field creates different kinds of dipoles. Dipoles means that you have one positive and one negative set, and this set is known as a dipole moment. You can better understand it from this visualization, that if you have this dielectric slab, it's a, let's say, a slab over here, and you apply an external electric field. So the electric field is going to agitate the charges inside the dielectric material, and you can see that dipole moments are created. So one dipole moment is this, the second dipole moment is this, so on and so forth. So this process of creation of dipole moments is something we called as polarization. So this complete process where the dipole moments are created, we call this as polarization. And you can see that polarization is dependent upon the area. So we saw previously that a dipole moment was represented at small p is equal to the charge and the distance between them. If you add all these dipole moments shown over here, you can sum them together into a single value and represent it by P of I. So the total dipole moment is basically sum of all small dipole charges, and the process from which this combination of dipoles are created, we call this as polarization, where polarization is defined as limiting delta V tends to 0 and sum of all of the polarization or dipole moments, and delta V tends to 0 means that the space inside this slab squeezes to just a single point. Maybe it can be this point where we have only one moment existing. So this is known as polarization. Now polarization can be related to electric field and electric flux density as such, that we know that electric flux density is equal to epsilon into E, and you can also add polarization. This means that you are showing a relationship between the electric flux density, electric field intensity, and the polarization. Again, we don't want to go into the proof of this, but this equation is something that you should know. And then there is another relationship directly between polarization and electric field intensity, which is represented as equation B, where Xe is called electrical susceptibility of the material itself. Sometimes this is also known as chi. Its value is written as Chi. So this is the symbol of electric susceptibility known as chi. And finally, if you combine A and B, so this is the complete equation where we can get the relationship between the fields and the polarization. So if we have D is equal to epsilon E plus rho, so you just input B into A, so you get this form of the equation, where this is another representation of the electric flux density and electric field with the polarization variable chi, which is written as Xe. So this is the chi symbol that we are using. Again, these equations are needed for solving the problems, but we don't want to prove them at this stage of this lecture. So let us look at a problem where we can utilize these equations, and here we are asked to find a few things. Okay, so a dielectric slab has a relative permittivity of 3.8, so this is E of R, and we have an uniform electric flux density, so the value of D is given 8 nanocoulomb per meter square. If the material is lossless, we need to find what is electric field intensity, then we need to find the polarization, then the average number of dipoles per cubic meter. So this is basically 1 by delta V, because the relationship between dipoles is basically the potential difference between them. If the dipole moment is this, so small p is over here. So let us solve this. This is a very simple problem. We need to find, in the first part, the electric field intensity. So electric field intensity in magnitude is required. We know that electric flux is equal to E into E, or E naught into E, where we can further simplify this E into value of absolute permittivity, relative permittivity with the electric field intensity, and thus from here we can find E. So E, electric field intensity, is going to be the value of D, which is 8 into 10 raised to power minus 9, divided by the permittivity 8.85 into 10 raised to power minus 12, and multiplied by ER, which is 3.8. So once you do this, you get the value of 237.7 volts per meter. Again, this is the magnitude of it. Then we need to find in the second part polarization. Again, it's the magnitude. So polarization, we can simply use the value that polarization, the relationship of polarization with electric field intensity is basically chi with the permittivity and E. So this is the equation that we have used, the equation B. So we have all the factors, just input the value of chi. So the value of chi is missing. So how can we find this chi? So chi, we can find it from, if you go back, this is what we can use. So chi plus 1. So we can say that permittivity is equal to chi plus 1, because ER is given to us. Then the value of chi is equal to ER minus 1. This is 3.8 minus 1. It is going to be 2.8. This is the value. Just incorporate it in the value of P. So it is going to be 2.8 multiplied with E, 8.85 times to the minus 12, and the value of E is 237.7, and it comes out to be 5.89 into 10 raised to power minus 9 coulomb per meter square. So this is the value of the polarization. And finally, in the third part, we want to find, so we have been given the value of dipole moment, so this is equal to 10 raised to power minus 29, and we want to find the total number of dipoles per cubic meter. So the equation for this is not discussed in the book, but this is for your understanding. It is basically 1 divided by delta V equals to polarization divided by the dipole moment. So this is equal to 5.89 into 10 raised to power minus 9 divided by 10 power minus 29, and it comes out to be 5.89 into 10 raised to power 20 per meter cube. So this is a new equation for you to know, and this solves the problem. So now let's come to the second part, and that is the boundary conditions for dielectric materials. So previously we found the boundary conditions for conducting materials, where we said that the tangential components of the fields will be 0 and the normal component will be the surface charge distribution. This is for the boundary condition between conductors. Now if you want to find the boundary conditions of dielectrics, so we are going to have the final solution as such that the normal conditions will be the same and the tangential conditions will also be the same. How so? Let us look into this. So again, we need to do the two things, that is, we need to find the tangential component and then the normal component. So for the tangential component, we stick to finding the E field along tangential line, and if we know E field, then dt will be figured out. For the normal component, we'll find d of n. Once we know d of n, then E of n will be extracted from there. So we start with the tangential component, and we take use of the same graph that we saw previously. So we now, in this scenario, we have two dielectrics. So the first region is a dielectric material. This is region 1, so let us call this E1, and the other material is also dielectric 2, let us call this E2, and this is as usual our boundary between them. So we stick to the same images. Let us say we go for the orientation of boundaries or the materials as such. So we stick with the rectangular function, a closed loop for both of the materials. For E it is going to be A, B, C, D. The width will be delta W as we saw previously, and this time the height is going to be negligibly small. So one condition that we are going to use for here, that the height is almost zero, because we have both the materials which are dielectrics, so there is no conductor this time. Second, we are going to stick to the cylinder as we saw previously, and again the surface will be delta S over here, and the electric field is leaving, or in this case electric flux density is leaving. Let us name the values. So this is now dn for first, and this is dn for 2. Tangential components for the first will be, if I draw the tangential components, let's say for both the cases, we have E field over here, its tangential component over here for 1, and the tangential component for 2, so ET2. And similarly the normal component will be E and 2, and the normal component of this will be E and 1. So for the first it is 1, and for the second it is 2, and the electric field is something like this. So this is basically the variations. Again for this it is going to be ET2, and the tangential component will be ET1 for this scenario, and the height is negligible over here, or it is 0. So let us first do the tangential component. So let us do the tangential component number 1. And see what will be the equation for the tangential component. So let us draw the boundary again for simplicity. We say that this is the electric field which is basically moving over here, then its components will be ET1. So this is ET1, and the tangential component over here is ET2. The normal component over here will be EN2, and the normal component for this will be EN1, and this is our boundary. This is region, okay, let's stick to the same. This is region 1, this is region 2. This means then this is region 2, this is region 2, this is region 1, and this is region 1. So now we have defined the tangential and normal components. Our focus will be on the tangential component. So in order to solve this, again we are going to use this rectangle over here. So our rectangular, let me draw the rectangle over here so that we can easily map it. This is A, B, C, D. Tangential components over here is ET1, and for this is ET2. Okay, so again it's a closed loop, so we're going to use the conservation of energy equation where E dot dl equals to 0, and again we are going to find the location from A to B, B to C, C to D, and D to A, which should be equal to 0. Now in the first path from A to B, so we are moving, so let me now use a highlighter for this. So now we are moving in this path A to B. So for A to B, our first value will be, we are moving along the tangential 1, and the width is delta W. Then we are moving from B to C. Now this is the path, so we are moving in the opposite direction to the normal. But since the height, so you have to remember that in this scenario delta H is 0, because it's a very small height, or it is approaching to 0. So in this case, when we move from B to C, automatically the En multiplied by delta H will be equal to 0. Then we are moving from C to D. So C to D, again I'm going to use a highlighter. This is now our path C to D, and it comes out to be plus, it is opposite to A to B. So whatever we had there is going to be opposite, which is going to be E T of 2 into delta W, because we are in the second region, we are moving in this direction. And again, when we move from D to A, height is 0, so automatically it will be 0, and the output will be 0. So this means that we will get the value of Et delta omega minus Et2 delta omega is equal to 0. So omega and omega will cancel out. We will have Et1 is equal to Et2. So this is the proof that when we have two dielectric materials, the tangential components are equal. Since the tangential components are equal, then what about the electric flux density, or the tangential component of electric flux density, which is equal to epsilon into T. So we can say that the E is equal to d by epsilon. So the tangential component of 1 divided by tangential component of 2 is the ratio of the permittivity. So this is the electric flux density's tangential component, which means that this is discontinuous. What does it mean? It means that if the electric flux density is moving from E2 to E1, it is dependent upon the material. It will not going to have the same value as we saw previously in the conduction case. What does it mean? If you remember the equation for the conductor case, in the conductor boundary conditions, the value of the normal was equal to rho of s. Then it meant that the value of the normal was equal to the surface charge, but here the value of the electric flux density or tangential component is dependent upon the material. So d1 is dependent upon this material's property and d2 is dependent upon this material property, and the value of tangential component for the electric field will remain the same. So this is what it means. Now let's come to the normal component. So now the second part, the normal component. What is the equation for that? So for the normal component, let us draw or visualize this. This is the boundary, and this is region 1 with E1 permittivity. This is dielectric E2, and now we are going to use the Gauss's law. So we are going to take the cylinder. This is the surface delta S, and the charges are obviously on this surface itself. So this is something we can know. Now the height is delta H, but again the height is equal to 0. It's very small height, and the electric flux density is over here. Its component is over here. So let us call this dt1. The other will be dt2. So the dt2 will be over here. So let me call this as dt2. And the normal component is dn1, and the normal component for this is dn2. So this is what we are having. Now applying the Gauss's law as we did previously for the conductor case. So we know that the Gauss's law is the closed surface integral d dot ds is equal to the total charge enclosed. Now in this scenario, what will be the integral? How many charges are on the top side, how many are on the bottom side, and how many are on the sides of the cylinder, that equals to the total number of charges. We know that the sides will be 0 because the height is 0. Then there will be charges on the top and bottom. In the conductor case, bottom didn't have any charges because it was inside the conductor, but here it's a dielectric material E2, so the charges are going to exist in the bottom side and the top side. So what is the equation now for the top side? We know that we have delta S, and the electric flux density is leaving, which is normal to the surface. Then we have minus the normal to the lower or bottom surface, and how many charges are there? Rho s into delta s. So this is basically the amount of charges. This is basically leaving electric flux, and this is entering the cylinder. So this is the representation of the charges. Now we know that the no free charges exist on the surface. So we have seen that the charges will not be existing on the surface. So here, because dielectric materials have charges inside them, not on the surface, which means that delta S will be cancelled out, and the value that will be left will be dn1 minus dn2 is equal to rho of S. Since rho of S is equal to 0 because no charges exist, so we can say that dn1 is equal to dn2. So the normal components of the electric flux will be the same, but the En1 will be equal to En2. So this is again a discontinuous, yani electric field will be discontinuous because of the different materials, but the normal component of D will be the same. So this is the proof for the normal boundary condition between E and D when both of the materials across the medium are dielectric materials. Now let us look at a problem and see how can we utilize these kind of expressions of the boundary conditions when solving the problem. So here the question, we have region 1, Z is less than 0 of uniform dielectric material for which the permittivity is 3/2. For the second region the permittivity is 2. The electric flux density is given as such. We need to find the normal component of D, the tangential component of D, its magnitude, its vector form and its magnitude in part C. Then what is D1, the total electric flux, what is theta 1, and what is the polarization value. So in order to solve such kind of problems, you first need to visualize it. So it means that if we have a boundary, the boundary is between two dielectric materials. So this is our boundary. Now which material is taken as boundary or region 1 and which is taken as region 2? So always remember, the region 1 is that region that has a higher permittivity. So this is going to be my ER1 with the value of 3.2, and this is going to be my ER2 with the value of 2, which means that this is the region for Z greater than 0 and this is the region for Z less than 0. So we have to always keep that region on the top that has more permittivity. Now if D1 is something as a normal, let's say if this is D1 and it is coming and D2 is coming from here, so this is D2. So the normal component of this D1 will be DN1. It is making a certain angle theta, and the normal component with respect to D2 is something which is making an angle theta. So this is DN2. So this is the angles made. So this is theta 1, this is theta 2 with respect to D1 and D2, and this is the region that we have. So our region is basically in the XY plane and Z is equal to greater than or less than 0. Now what we have is, we have the value of D1, which is minus 30 A of X plus 50 A of Y, so unit vector, plus 70 A of Z nanocoulomb per meter square. So now if we have a value of D, we can decompose it into its tangential and normal component. So D1 can be decomposed into its tangential plus normal component. So what is the tangential component? The tangential component is lying along, we can see from the question that Z is the region where the uniform dielectric materials are placed, which means that our tangential component will be along X and Y. So the dt will be having a value of minus 30 A of X plus 50 A of Y. This is my tangential component. And what is my normal component? The normal component will be 70 A of Z. So this is my normal component, and that's it. Okay, so we have this nanocoulomb, so it means that this portion will have a value of 10 raised to power minus 9 as well. So this is how we disintegrated our vector D into the tangential component and the normal component. Once we do this, our analysis becomes quite easy. How? Because we need to find in part A what is the normal component of D of n. So it's straightforward. Dn1 is going to be 70 into 10 raised to power minus 9 along A of Z. That is the answer, coulomb per meter square. That's it, we got the answer for this. What about the second part? So in the second part, so this is the solution of part A. In the second part, we have to find the dt1. What is the tangential component? We already know tangential component is minus 30 along A of X plus 50 along A of Y into 10 raised to power minus 9. And what you want, so it is nanocoulomb per meter square. That's it. What about the third part? What is the magnitude? So magnitude, you just take the magnitude of dt1. That's it. So it comes out to be 58.3 nanocoulomb per meter square. That's the third part. What about the fourth part? You need to find d1. So d1 we already know. If you want to find the magnitude of it, okay, we find d1, its magnitude. d1 is already known to us, so you just take the square of all the three terms. The answer will be 91.9 into 10 raised to power minus 9 coulomb per meter square. That's it. So what we did for D1, we know that it was basically the under root of 30 square plus 50 square plus 70 square, and this is how we got the answer of D1. What is so this is D. What is part E? So for part E, we need to find the angle between them. So the angle between them, okay. So we know that theta 1 is going to have a greater angle because its permittivity is higher compared to theta 2. So we can apply that. So what is the boundary condition? So we know that theta 1 is greater than theta 2 because ER1 is greater than ER2. With this condition in mind, if we go back to the figure, we can see it is making a normal with the base, so we can apply the cos tangent theta. So dn1 is equal to the magnitude of d1 with cos theta. So we can say that theta is equal to cos of inverse, the value will be 70 into 10 raised to power minus 9. This is the value of normal component of d divided by d1, 91.9 into 10 raised to power minus 9. Once you solve this, the answer will be 39.79. That's it. This is the answer. We can verify. This is the answer. And finally, we need to find the polarization. So polarization, this is another formula that will be helpful for you, is you take the permittivity difference divided by the permittivity and multiply it with the electric flux density. So this is a new formula which you can utilize. So the answer will be 3.2 minus 1 divided by 3.2, and the value of D vector is 30 along A of x plus 50 along A of y plus 70 along A of z into 10 raised to power minus 9, and the answer comes out to be minus 20.6 A of x plus 34.4 A of y plus 48.1 A of z nanocoulomb per meter square. That is the answer, and this concludes the problem. Let us check the answer. Yes, minus 20, 34, 48. I'm getting the same. Yes, minus 20, 34 and 48. So this concludes the solution to this problem. Now let us look at another question, which is continuation of the previous problem, and this will be the last problem that we are going to solve. So again, with the data provided in the previous problem, we need to now find the normal component of the second region in terms of the electric flux density, normal component, tangential component, the magnitude, the polarization, and the angle of the second region. So we know from the boundary conditions of dielectric materials that the normal components are the same. So whatever value we got from the previous will be for the second as well, which is going to be 70 along A of z nanocoulomb per meter square. Then in the second part, we need to find what is the tangential component. So tangential component is basically equal to E2 by E1 to the first tangential component, and it comes out to be, so we can extend E to its absolute and relative permittivity values. So this is ER1, ER2 dot the tangential component. The E0 will be cancelled. It will be 2 divided by 3.2, and the value of D was the tangential component 30AX plus 50AY, and once we solve this, the answer comes out to be minus 18.75 along A of z plus 31.25 along A of y nanocoulomb per meter square. This is the solution to the second part. In the third part, we need to find what is the value of D2. So for D2, it is the original value of the D2 signal, which was basically this angle over here. So we can break it down into its tangential and normal component, which will be D2 tangential plus D2 normal, and it comes out to be, so you just add them, tangential component, already we have it, then it will be minus 18.75 along A of x plus 31.25 along A of y, and then the normal component is, as we saw in the first part, it is 70 along A of z nanocoulomb per meter square. Finally, we want to find the polarization of the second region. So again, the equation we saw earlier, ER2 minus 1 divided by ER2, and you multiply it with the D2 value, and it comes out to be minus 9.375 along A of X plus 15.6 A of Y plus 35 along A of Z nanocoulomb per meter square. And finally, we want to find the angle theta. So it is going to be the normal vector to the magnitude of the second value with cos of theta 2. So theta 2 comes out to be, I'll just write the value. It is going to be cos inverse, this dn2 is 70 into 10 raised to power minus 9 divided by the value of 78.9 into 10 raised to power minus 9, and it comes out to be 27.5 degree. So this is the solution to this problem, and that's it. So we have completed the fifth chapter with all the important equations and their associated problems.